Greetings, student. This is a recording of one of Garnett's online math lesson classes. You have been granted access to watch this video because you're a paying student and I have seen it fit to provide this recording to you. However, it is important that you know you're not allowed to share this video with persons outside the lessons. This policy is so that my services are kept only to my students. Thank you, and I do hope you enjoy and learn from this video.
So most of us have done area of a triangle and area of a parallelogram already. So this is just recall. Like with the Venn diagram stuff, is just recall. So most of what I'm teaching you so far seems to just be recall, right? So and that is a good thing. It means that we're sharpening what you already know. Good. So let's first talk about uh, um, let's first talk about the area of a triangle. Now, I know most of us are usually accustomed to this one. This is the one we learned from birth, but then we start getting into some two other complicated ones. All right, now there are three formulas for calculating the area of a triangle. Now, depending on the information you're given, depending on the sides and so on, that will dictate which one you will use, right? It's not always, you don't always get lucky to pick which one you want to use. Sometimes you have to use this one, for instance, or this one, right? Personally, I hate this one. This one is the most troublesome one to do. You gotta sit down there and do a lot of math, right? Minus this and add that divided by 2. This one is the longest one to work with. So usually you try and hope that you have to use either this or this, but you can't forget this one because as I will show you just now, this one will bail you out when you don't have information with regards to base and height. This is one of the most important things, right? So now I will go through each formula step by step, and we will work an example, and I will explain what I will do. And from now going forward, when I show you a formula, most of the formulas that I will show you in maths, I will do a bit of explanation on how they came about, right? Because there are logical reasons for them. They didn't just, somebody didn't just sit down and decide area is equal to half base times height, right? I will do that for the area of a triangle, and I will do that for area of a parallelogram. I will also do that for some other stuff that we'll be doing on the measurements, right? So the first one, I'm gonna completely skip this one, half base times height. We already know this. I don't expect this one to be unfamiliar. It's just area is equal to half base multiplied by the height, and that is usually base, right? The base is usually the bottom and height, and I will explain base and height. That sometimes gets confusing for some students, right? Identifying the base, what is the base of a triangle and what is the height, believe it or not. So the first one is we're gonna go through the what I believe is the most taxing one first, and that's Heron's formula. Right now, Heron's formula says that area of a triangle A is equal to the square root of S, and this variable S is half of the perimeter of the triangle. So you need to find the perimeter of the triangle divided by 2, and that will give you the value of S, right? Now, it's the product of the difference between S and each side, right? So area of a triangle using Heron's formula is the square root of the product of S and the difference with each side, right? So you have S, and then, well, the square root first. You have S, which again is a half the perimeter of the triangle, open bracket, S minus A, close, S minus B, S minus C. And A, B, and C, I told you what these variables are with S. S is half the perimeter, but with A, B, and C, those are the sides of the triangle, correct? Right? Those are the sides of the triangle. Either this side could be yeah. All right. So one thing right away that should jump out at you is that you can't use this formula if you don't have the perimeter of the triangle. If you cannot calculate the perimeter of the triangle, then you can't use Heron's formula. One thing good about Heron's formula is that you can always use it once you have all the sides of the triangle. So that's two good notes you should remember. You can use it once you have all three sides of the triangle, but you can't if you don't have the perimeter, which is all three sides of the triangle. So you need all three sides of the triangle to use Heron's formula. As soon as you have all three sides of the triangle and you don't have, and you're not looking at the triangle with, actually, I will, when we go through all the formulas, then I will get back into identifying which one to use in which situations, right? So Heron's formula, you need all the sides of the triangle. That's the first thing you should notice, right? Now, A, B, and C, those letters, you're going to see those letters a lot of them referring to triangles. They're the conventional way mathematicians usually label triangles, and we will get into that a bit later, right? So A, B, and C are the sides of the triangle. Doesn't really matter which one you call A, B, and C. In this case, it doesn't really matter which one you call A, B, and C. I will teach you the conventional way of labeling the triangle, not to worry. But let's work an example using Heron's formula. Now, this is a triangle. Now, one of the first things, you shouldn't go to Heron's formula unless you have to. As I said before, it's a lot of work. You gotta find the perimeter divided by 2. Then you gotta go, use the product of differences and square root it. Right? That's a lot of work. So don't go and use Heron's formula unless you need to. Right? So looking straight at this example, this is an example where I don't know, I have forget that this is here. This shouldn't be here, because with this one here, there's an easier way to solve it with this angle here, right? So let's say the angle wasn't here. Yeah, let's say the angle wasn't here. We have all three sides of the triangle, right? The Heron's formula is the only formula you can use. It's the only one you can use. Now, what some students mix up with is that the base, identifying the base and the height of a triangle. Now, yes, this is the base of the triangle. This the bottom here, which is 2.7 cm. This is the base of the triangle, right? So what I'm trying to explain is why you can't use half base times height, right? So this is a base of a triangle. Yes, so you have the base, but you also need the height, and this is the height of the triangle. The height of the triangle is perpendicular and will always be perpendicular to the base. So if you didn't know that, the height is always perpendicular to the base, or you can think the base is perpendicular to the height, whichever one. Rihanna, what do I mean by the height is perpendicular to the base?
Sir, hold on, I'm going to check Google.
Somebody answer faster than Google over here. What do I mean by the height is perpendicular to the base? What I want you to get at is, what does perpendicular mean?
Sir, it's like lines that intersect.
You're intersecting, yes. I mean, they connect, but there's an important feature, and the
At
word
90
is
degrees?
90 degrees. There needs to be a 90-degree angle between the base and the height. If there is no 90-degree angle there, then it's not the height, nor, well, you might have the base, but you don't have the height, right? So I don't have that on the slide, but always remember that the base, or whichever one you want to look at it. So let's say the base will always be perpendicular to the height. Right? Forgive my atrocious handwriting. This not just goes for triangles, it goes for anything. The base will always be perpendicular to height. And perpendicular just means that they are at a 90-degree angle. So if it was a right angle triangle, usually those are the ones where you have your base and your height. you're fine. Or if I did this, I drew a perpendicular line to the base, right, which has a 90 degree. This would be the height of the triangle, right? Be very careful with this. So don't let me ever see you guys using these sides as the height. If it's a 90, if it was a 90 degree, right, where you have that 90 degree already in the with the triangle, then yes, this is the height and this is the base, right? Depending on how you look at it, this is the height and this is the base, and there's always going to be a 90 degree between the baseline and the height line, always and forever. So once you don't see that 90 degree, it's usually, you can guarantee that a 90 degree symbol will be there. If there's no 90 degree symbol there, don't say it look like if it's 90 degree. Don't do that. If an angle is 90 degree, it will always be indicated. You will you notice that throughout CSEC. You notice that throughout CSEC. All the questions, if a triangle is 90, if there's a 90 degree within a triangle, it will always be indicated. So if you don't see that square that indicates a 90 degree angle, then the two lines are not perpendicular, which means that that line is not the height, right? So remember that the base is always perpendicular to the height. Let me just put a in bracket here. Perpendicular meaning 90 degree. Right? That there's a 90 degree between those two lines, a 90 degree. So we can't use, right? That is the base, but we can't use half base times height, right? So eliminate that. That's the easiest one to use. And once you can use it, I suggest you use that one first. But we don't have the height. We do have the base, but no height, so we can't use that one. And the other formula, we can't use that one because we need an angle for that one. And you will see that just now. So the only one that we can use in this scenario is Heron's formula, right? So Heron's formula states S is equal, the first thing you ought to find is S, which is half the perimeter. I know the perimeter is the sum of all the sides, right? So we need to find S again, or just a reminder of Heron's formula. First we find S, and S is half the perimeter. And remember, the perimeter is the sum of all the sides. So we just totaling the sides and then halving it, or dividing it by 2, or multiplying it by half, or multiplying it by 0.5. All of that just meaning half in it, right? So sum divided by 2, 4.95 centimeters. Now with measurements, usually there are measurements, which means they carry units. So all your answers should be in units. You will lose marks if you don't have your answers in units. So be careful with that. Make sure that you have your units. If we're using centimeters, we're using centimeters, right? So indicate the units. With anything in measurements, they are usually units. So make sure you indicate that. Oh shucks, this note is. We found half the perimeter, which is S. Then we need to go ahead and multiply S, like it says here with the formula. Just substitute the values. So S, A, B, and C can be any one of the sides. You can call this side A, then this one B, then this one C. Whichever one doesn't really matter. You will still end up back with the same answer. However, what you need to ensure that you're doing is multiplying S, open bracket, S minus one side closed, S minus the other side closed, and then open S minus the other side. So is the difference between S on each side multiplied by S, right? Now you all know how to add and subtract, so I'm not gonna waste time on that. So we just multiply, add. What you notice you end up here with is centimeter cube. You can, what students do, if you know area is centimeter square, right? Is usually a squared, as well, we use a metric system. So square, right? Centimeter square, meter square, anything square, area, right? So the units for area is centimeter squared. You can go ahead and use the numbers and just put the units at the end, right? At the end of everything, instead of writing the centimeter all the time inside here. You can just, if you know area, this is one way some people cheat the work. Instead of writing centimeters so many times, you can just write the numbers, and at the end here, just put a bracket. Yeah, you just put a bracket and put, area centimeters square. You end up with centimeters square. That's one way students should do work of writing centimeters that many times. And you can do that. Nothing is wrong with doing that, right? But going through it the long way, meaning I'm writing all the units, you will end up with centimeters to the fourth power. Reason being is because you have centimeters multiplied by centimeter, multiplied by centimeter, multiplied by centimeter. All right, so that means you're multiplying centimeters 4 times, so centimeters cube, 4 to the fourth power, sorry. All right, and then again, we have to multiply in those numbers as well. 19.78. We end up back with 4.45 centimeters squared, right? The square root knocks off, well, divides the 4 by 2. That's what square root does. Divides the power by 2. So we end up with centimeters squared. You could jump ahead and write the centimeters squared, right? Right. So the answer here is 4.45 centimeters squared using the Heron's formula. And don't forget that this statement here. I don't forget this statement here. It doesn't just apply to, it applies to all shapes, right? The base and the height is always perpendicular to each other. Any question? Now, the next formula is using the length of two sides and the angle between them. I'm not going to stress behind the name of this, but that's what it is. You're using the length of two sides and the angle between them. So what you need is two sides and the angle between them. The right away, that should tell you what you need to use this formula, right? So far we've covered Heron's formula. You guys already know area base times height. You need the base and the height to use that formula. And Heron's formula, we need all three sides to give us the perimeter so we can use Heron's formula. Now this final one, you need two sides instead of the three, and the angle between those two sides. In particular, you need the angle, the length of two sides of the triangle, and the angle between those two sides. So now here, you noticed I didn't give you an angle, all right? And again, we have our triangle conventionally labeled. So this is how the formula looks. It's area of a triangle. We're using this formula. It's half. That half comes up a lot, right? So a half AB sine C, right? It's, to be honest, being truly honest with you, it is actually in secret your A of base times height formula, but you're using some trigonometry, right? It is in secret your A of base times height formula, because that half there gives it away, but you don't have the height, and that's why we have these other terms, right? That's why you have these other terms. So half AB sine C, right? A and B being the length of those two sides that we spoke about just now, and C being the angle between them, right? Usually sine and angle. So half AB sine C is the formula here. Now, let me see. We haven't done trigs as yet. However, we're seeing a bit of trigonometry here with sine. Let me see those who know the term sine. Just raise your hand. You've seen sine before. You've used sine on your calculator before. Raise your hand. Let me see. All right, so there's. All right, so 5 of us have not used sine before. No, 5, 6. 5. Okay. All right, so sine is a trigonometric function that is on your, where's my calculator? You shouldn't come to math class. Oh, there it is. Setting a bad example. You shouldn't come to math class without your calculator. Yeah, but sine is a trigonometric function that's on your calculator. So you can only do these trig operations with your calculator. Back in the past, the students had to do it without a calculator. In the past, times were rough. So they didn't have calculator to do sine and so on. So they have to use a calculator. You have to do it, know them out your head. And you have to do sine and trigs, those trigonometry in your head, which is harder, right? As you can imagine. But sine is a trigonometric function on your calculator, and you can just think of it as, instead of like your normal arithmetic operations like square root and multiplication. Well, let me think of some better operations like square root and power, where you multiply, where square root, you're square rooting a term, or power, you're squaring a term, or that kind of thing. You can sine a term, right? And cos and tan. But I will get into those trigonometry later. But just know for now that sine is a trigonometric operation found on your calculator, you can use on the calculator, right? And we only see them with trigonometry, which is triangle geometry, right? But moving on from that, once again, the formula here is half AB sine C, which means A and B can be two sides of the triangle, and C just has to be the angle between them, sine the angle between them. So now looking at this triangle, yes, this is A and this is B, but as I said before, this doesn't really matter once you have the length of two sides and the angle between them. So in this case, the formula here is half AB sine C, which is the angle here, right? That's it there. But it can be any one of the two sides. You can have BC sine A, right? You can sine the angle. So don't bother with these letters. I don't want you to focus on that. They're not important to remember. I say that I still will teach you them, but they're not what's key here. What you need to focus on is the fact that you're looking at the length of two sides and the angle between them. Think of it as a V, right? You're looking at a V with an angle between them, right? Good. So let's look at an example. Enough talking about the formula. Let's actually use it. So using we can use Heron's formula here. Right away, you see we have all three sides. So Heron's formula, check. Area of base times height. Well, half base times height. Sorry for that. Half base times height. We can't use that because, as I said before, the base, let's say this is the base, right? This is the base. The height needs to be perpendicular to the base. So this side nor this side is the height of the triangle, right? So what the other option, we're not going to use our formula, but the other option would be to use this formula, half AB sine C, right? Which is less work than Heron's formula, right? You will see that. So 3.7 centimeters and 3.5 centimeters are the length of the two sides that are enclosing this angle, right? So the angle here is for the 3.9 degrees, and the length of the two sides that the angle is between is 3.5 and 3.7, right? So right away, half, right? The area of the triangle is half the length of the two sides, which is this guy and this guy, 3.7 and 3.5. So multiply 3.5 multiplied by, I'm saying 3.5, I'm pointing at 3.7. So yeah, multiply 3.7 by 3.5, and then the angle between them, which is 3.9 degrees, sine 3.9 degrees, right? And again, sine is in your calculator, right? It's an operation in your calculator. So just plug this in your calculator, you should be fine. Now, one thing I want to no, I will do that when we're doing tricks, don't worry. So half 3.7 centimeters multiplied by 3.5 centimeters sine for the 3.9 degrees. What's the answer here? Got 4.49. Those are the three, right? Those are the three formulas for calculating the area of a triangle, right? We went through two, well, I went through two of them with you because I know most of us are familiar with the half base times height. So remember when to use them, remember how to use them. Sides are, labeling the sides are not that important. We'll go through that just now, but what's important is you remember the principle, right? Here you're multiplying half base times height. You need a base and the height, pretty basic. Here with the second one, half AB sine C. AB refers to the length of two sides, and C is the angle between those two sides, right? I can't emphasize that enough. It's the angle between those two sides. Now, last but not least is Heron's formula, which is square root of the half the perimeter, which is the same thing as going on here. This is just half the perimeter. Multiply the product of the differences of each side, right? That's how we're gonna say. Right, so those are the three formulas for calculating area of the rectangle, the triangle, sorry. Now, one more thing that we keep seeing, what we keep seeing is that the triangles are labeled A, B, and C. Those three capital letters. That's the way we've been doing it for a while now. And it's the way you see it labeled in your CSEC questions. You'll usually see A, B, and C, P, Q, R, those conventional letters. But one thing you got to remember is that each vertex of the triangle is labeled with a capital letter, right? This is a conventional way that we label the triangles. Right? And you will notice it when you go forward, you look at past papers, textbooks, you will notice this is the convention, right? So each vertex is labeled with a capital letter, just by sheer, I think it's just repetition. We've been using A, B, and C. So each vertex is labeled capital A, capital B, and capital C. Right? That's the first thing here. I just said that. So we have each vertex of the triangle labeled A, B, and C. This is just, I just choose to put A, B, and C like this. It could be the other way around. That's not relevant. Now, the sides, that's the vertex, and the vertex is associated with the angle right adjacent to it or right next to it. So any angle that's here will be called angle capital A, right? The capital A is the label for any angle here. So, I don't think that's in the slide. Well, write it in. Right, so A, yes, that's the label of the vertex, but what's more important is that it's the label of the angle that's between there. So B refers to the angle between here, capital B. Let me use it. Let me say it correctly, capital B and capital A, emphasis on capital, right? So it's usually the vertices or the angles of triangles are usually labeled capital letters, right? By convention, it's A, B, and C. Now, with the sides of the triangles now, with the sides of the triangles now, it's the common letter of the angle adjacent to that side, right? So the vertex here is capital A, so this side is labeled common A, right? So you just have to go to the capital letter, slide across the angle, the side is facing, right? Usually the side is facing, or you can think of it as the line the angle is siding, the line the angle is standing on, right? It's labeled common A. So across here is common A, across here would be common C, across here common B. So that's how the sides are labeled. Across here common B, across here common C. So again, vertices are labeled with capital letters. That's what's in the notes, right? That's what's in the notes here. The vertices are labeled with the capital letters A, B, and C by convention, and the adjacent side or the opposite side, not adjacent, sorry, the opposite side to that vertex is labeled the common letter of that, whatever letter it is, right? Following.
Yes, sir.
As you know, so if we go back, so I will go back to that slide, not to worry. If you go back to this is what you see here. And by the way, this is taken directly, this image is taken from the cover of the CSEC maths paper. Both paper 1 and 2 from now on are coming with the formula sheet, right? So this is just the area of the triangles part of the formula sheet, and you see here it has the three formulas. And when you look at the triangle, that I have here. And you notice here they indicated to you that the base is perpendicular to the height, right? It has a 90-degree here. So this is the height of the triangle, right? I explained that before. But what you notice here is that that is indeed the case. Capital letters on the vertices of the triangle and common letters on the side opposite that capital letter. So this is common C, this is common B, this is common A. That's usually how you label it, right? That's going to become important as we keep looking. Generally, it's not that important. I keep saying that. That's to me, right? To me, it's not that important. However, what we need to keep in mind is how they're labeling it, right? Because it's not randomly, they're just randomly picking letters and randomly naming it. There is a system to it, right? Capital letters on the vertices, common letters on the sides. The same thing is stated here. This is the same thing. However, they're in this case, the capital letter A, B, and C, they're usually random. I think they're usually in this direction, clockwise. But right? Now, if it was a right angle triangle, what you can guarantee is that they're going to label this side C. You can almost guarantee that the hypotenuse is going to be common C. Now, if this side is common C, use the common letters, right? They use the common letters. So C is usually the hypotenuse, and that's the diagonal on of our right angle triangle. And here will be capital C, and they usually label here A, right? That's the perpendicular height, and B as a base, of course, and B as a base. This is the usual way they label the right angle triangle, right? Again, that's just the convention, right? This is just the conventional way we do things, right? So common C as the hypotenuse, A is usually the perpendicular height, and common B is usually the base, right? Now, you use the same metric, the same system we did before, where the opposite side, the vertex opposite that side is the capital letter, right? So this side would be capital B, this vertex would be capital B, this vertex would be capital A, and that one capital C, right? So you have your A, B, and C, right? So you're still using this system. However, what will stick is that this side will always be C, this side A, and this side B, right? They usually that's the case, right? Again, these are just the conventional ways that we've been labeling triangles. Right. So before we move on to parallelograms, I will give you a 10-minute. I'll give you a 10-minute break. You can take this now. Don't forget it. And your break starts area of a parallelogram. Right. Now, area of parallelogram is just, let me just say, you just take what you learned from area of a triangle and multiplied by 2. That is essentially what they did with the formulas. They just took the formulas for triangles and just multiplied it by 2 and called it George. Because as you will see in a second, a parallelogram is just 2 triangles. So let's look at the two formulas. There are 2 formulas for the area of a parallelogram, unlike triangle, which is 3. So for this, you have A is equal to base times height, where B is the base of A is equal to, there it is. Yeah, so area of a parallelogram is equal to A is equal to B times H, and B is the base of the parallelogram, and H is the height of the parallelogram. And as I said before, well, they should be indicated here. This memo is not a 90-degree unless you see 90-degree. So A is equal to B times H, meaning that the base and the height, remember, the height is always perpendicular to the base. So this is the base of our parallelogram. Therefore, and this is the height, right? It's 90 degrees to that base. Right? Doesn't matter where on the line it is. Well, it's usually gonna be here or here. Yeah, but this is the perpendicular height of the parallelogram. And you can just multiply those two and it gives you the area of the parallelogram. The second formula is area of the parallelogram is A is equal to AB sine C. Similar to this area, this base times height, similar to the triangle, and AB sine C, similar to the triangle, right? The only difference is what's missing. Somebody shout it out quick. What's missing from the formula compared to the triangle?
There's no half.
There is no half, right? And the half is missing, right? That's the only difference between these formulas. So once you could remember your formulas for the triangle, just remember to just take out a half from the base times height and the AB sine C, and you have the areas for the parallelogram. I believe it's going to be on the formula sheet, but once you remember this, you don't even need to go to the formula sheet, right? So just now the reason why, and that's the reason I'm not going to get into why that is so, right? Why is this observation that we're seeing here that the half is just gone? And it has to do with what I told you, which is that a parallelogram is basically two triangles, right? So if we bisect, let me do this the right way. Let's say we bisect let's say we have a parallelogram here and we bisect this parallelogram. Let me get, right? This is what I'm about to say. So let's say we bisect the parallelogram in half on a diagonal, diagonally bisect the parallelogram. So, and we end up with, you notice we end up with a triangle over here and a triangle over here. In other words, we broke the parallelogram into two halves, right? Two triangles, right? So that's essentially why, forget about all this. That is essentially why the formulas are the same, right? Well, not the same without the half. So this is half. So if you wanted to find the area of this triangle, you would go half AB sine C. I mean, if you wanted to find the area of this other side, this triangle over here, you'd go half AB sine C, right? The same formula. Now I'm not using the label in the AB refers to any two sides, right? I'm using AB twice, right? So now what you'll notice is that if we want the area of the entire parallelogram, a half plus a half will make 1, or a half times 2 is 1. So you just end up with a half plus a half will just give you 1. So you just end up with AB sine C. So because two triangles create the parallelogram, the half and the half goes out, right? Now that's where the half came out. It didn't just disappear. It's because a half plus a half makes 1. So it's just 1, right? And it doesn't make sense multiplying anything by 1 because anything times 1 is equal, still equal to the original expression, right? 5 times 1 is still 5. So that's where the half went. That's where the half went, right? Yeah, I said this before, right? Right, so these are our two formulas, right? It both went away here and here for the same reason. For the same reason that a parallelogram is just 2. And remember, B refers to the length of two sides and C the angle between those two sides. Right? Don't forget that. It's the same thing with the parallelogram. An example. Let's look at an example real quick. We can use either one of the formulas. So we use both formulas and get the same answer. You get the same answer, right? You expect to get the same answer. So let's use the first one. So what we want to do is calculate the area of this parallelogram, POQZ. I didn't use any convention to label a parallelogram. Now, using the first formula, which is the easiest one to use once you have the base and the height, usually it's the easiest with the triangle and with the parallelogram. A is equal to base times height. We have the base. The base is 8.5 centimeters, and the height, which is a perpendicular length, right? This is perpendicular. This line here is perpendicular to the base, right? Usually these lines are, right? Any line going like this is perpendicular. Any vertical line, I should say, any vertical line is perpendicular to a horizontal line, right? So vertical lines are perpendicular to horizontal lines, right? However, this line is outside, right? So there's no need to put the 90 degree here, right? So the perpendicular height is 6.4. It's labeled for you, and the base B is 8.5 centimeters. So the area of the parallelogram is just 8.5 multiplied by 6.4, 54.4 centimeters squared. Right? Remember, we're looking at measurements. We need to put those units in there. Right? So that's the first formula. Let's use the second one, which more or less says the area of the parallelogram is the product of the two sides sine the angle between them, right? So the two sides sine the angle between them, AB sine C. So now we have two sides, right? We have two sides, we have two sides. One thing you need to remember about the parallelogram is it's a parallelogram, right? Like with your rectangle, parallel sides of a parallelogram are equal, right? So if this side is 8.5, this side will be 8.5. Right, so if this side is 8.5, then this side will also be 8.5. And if this side is 7.4, this side will also be 7.4. Right, so parallelogram. So what you need to note here is that parallel sides of a parallelogram are equal. It's called a parallelogram. Right? And technically a rectangle is a parallelogram, so that's the case. Another thing we need to note about the parallelogram is that adjacent angles add up to 180. What do I mean by that? That means if these are two things about the parallelogram that you need to remember. Not just that, yes, opposite parallel sides, right? Opposite sides are parallel, but that the parallel sides are equal, right? The parallel sides of the parallelogram are equal, and also that the adjacent angles are supplementary, meaning that the adjacent angles are add up to 180. So if we're looking at we have one angle here, which is 120 degrees. The angle adjacent refers to the angle next to it. So here and here, these two angles. If you want to know the angle here, you just need to, since this angle plus this angle, which are adjacent to each other, are supplementary, meaning that they add up to 180. If I want to know the size of this angle, you just have to subtract it from 180. 120 minus 180 is 60 degrees, right? So this angle here would be 60 degrees. And this angle also would be 60 degrees. And this angle here would be 120 degrees. Because again, adjacent, this one rule. So once you know one angle inside the parallelogram, you essentially can figure out all the angles, right? Because the parallelogram, because of the geometry of the parallelogram. So just remember these two facts, these two features about our parallelogram. Not just the sides are parallel, but parallel sides are equal, and the adjacent angles add up to 180. Right? So this angle Z and angle Q will add up to 180. So just minus one of the angles from 180, and you will get the adjacent angle. Right? So That's another thing. But however, so we know we can use, and this is where this fun fact that I skipped real quick, I skipped here, right? Fun fact, it doesn't matter which angle you use, whether it's A, B, C, or D, you'll get the same area, right? Fun fact, it doesn't matter if you use any one of these angles, but you only see two angles, 120 and 160. It doesn't matter where you plug 120 or 16 here. Because of trigonometry, you're not going to get into the logistics, but because of trigonometry, you will still get the same answer, and you can try that out for yourself. So the tool, however, let's use the what we've been doing all the time, which is to use the side and the angle between them. So we have 7 points. Yeah, so let's use these two sides, right? These two sides, 8.5 and 7.4 centimeters. So 8.5 multiplied by 7.4 multiplied by sine the angle between them, which is 120 degrees. You'll get similar answer to before. One point off is okay. It's mostly because of the trigs. The sine is the reason. However, another way you can do this, and I can guarantee you'll get the same answer. Or another way you can do this, so go area is equal to the same. If you use these two, you notice all the sides are the same. It's practically two lengths you're looking at. So if I were to use these two, let me shade them in yellow. These two sides, 8.5 and well 7.4, is the same size, right? I know that. Multiplied by 8.5 centimeters. Notice the sides don't change. However, yikes, I used those two sides and not the 160. So these two sides I should be saying. Apologies for that. But yeah, these two sides and the angle, and I use the angle here, which is 60 degrees. So sine 60 degrees, you will get back your 54.5 centimeters squared. You will get that back. Reason being is because I said I want to explain it. But it's because sine 120 degrees is equal to sine 60 degrees. They're two different numbers, but they give you the same answer, right? Trigs. So because sine 120 and sine 60 gives you the same number, it didn't really matter whether you put 120 or 60 over here. And that usually happens when you're looking at supplemental angles, right? You will see that pop up when you look at supplemental angles. But I'm taking you to another level that you don't need to know at CSEC. So let's just forget about this. And just remember the length of the two sides and the angle between them.
For the 4.9 you had there, sir, and then when you subtract them, you got 4.85.
But I didn't even notice that. That should be 4.9, correct? 4.95, sorry. That is correct. That should be 4.9. Thank you very much. The correct values. Believe it or not, I remember teaching this last year and that being a correction that needed to be made. I never made that correction. As you can clearly see, I never made that correction. So thank you. I think I did the same thing where I left it. Any other questions though, or queries? that's gonna be it for today. Have a best night as usual. Long as you have to, and take your vitamin C's. Next session, next week, we'll move on to circles. Same, so changing shapes, right? We move on to circles, measurements again, looking at area, that kind of stuff.